All right, let's just jump right in. We live inside this gigantic spinning spiral of stars we call the Milky Way. But have you ever really stopped to think about how tough it is to map something when you're stuck inside of it? I mean, it's kind of like trying to draw a map of your entire house, but you can't get out of the living room chair. So today, we're going to look at how we finally cracked that problem.
So it all starts with one of the biggest questions you can ask in astronomy, right? How did our galaxy get these incredible, beautiful spiral arms? But to even get a shot at answering that, to figure out its history, we have to know what it looks like today. And that means we need a map.
And, to even start making that map, astronomers had to solve this problem. A real head-scratcher that stumped people for literally centuries. I kind of think of it as our galactic blind spot.
Okay, so here's the deal. When you and I look up at the night sky, what we're seeing is basically a flat picture. It's two-dimensional. We can see where stars are, left to right, up and down, but we have no idea how far away they are. And without that one crucial piece of information, depth, you just can't build a 3D map. It's impossible.
And that right there, that's the key to everything. Being able to figure out the distance to things in space, it's probably the most fundamental piece of the puzzle you need to understand the true structure of the universe. I mean, without it, you can't tell if a star is just a little guy that's close by or an absolute giant that's incredibly far away. They could look exactly the same to us. And this quote, man, it just perfectly sums up the scale of the problem. Before we could measure these stellar distances with any real accuracy, we were basically flying blind. We were missing the galaxy's true depth, its shape. We were missing half the story. Literally, half the information was just gone.
So, to fix this, to fill in that massive gap in our knowledge, scientists needed something totally revolutionary. They needed a machine built for one specific purpose: to peer deep into the cosmos and measure the stars with a precision that was just unheard of. And that's where the hero of our story comes in, the Gaia spacecraft.
Yeah, Gaia. It's named after the ancient Greek goddess of the Earth, which is pretty cool. And what it is, it's literally the first machine humanity has ever built specifically to be a precision distance measuring machine on a cosmic scale. Its whole job is to get the addresses of the stars.
So the launch itself was just spectacular. A perfect ride into space. You could see the rocket stages just popping off as it climbed higher and higher. But, after all that excitement, the entire mission boiled down to one single nail-biting make-or-break moment.
And here it is. This was the whole ballgame. Gaia has these incredibly sensitive telescopes, right? And they absolutely cannot be exposed to the sun. So it had to unfold this enormous, super complex sun shield. If that thing failed to open, that's it. The heat from the sun would just fry the instruments. The entire mission over, before it even really started. It was, no exaggeration, a do-or-die moment. Well, thankfully, the sun shield deployed perfectly. Huge sigh of relief for mission control, I'm sure. So, now let's get into how this amazing machine actually works. How in the world does Gaia map the stars? The answer is, it's a really brilliant use of a very, very old technique: triangulation.
Okay, so Gaia doesn't just circle the Earth like a normal satellite. It travels about 1 million miles away from us to this really unique spot in space called L2. You can think of it like a gravitational sweet spot. It's a place where the pull from the sun and the Earth kind of balance each other out, which lets Gaia just hang out there without using a ton of fuel. And from that spot, it tags along with Earth on our journey around the sun. It gives it the perfect, stable platform for mapping the galaxy. Now, this is what's so cool about this. The basic idea is actually super simple. First, Gaia locks onto a star and measures its position against all the other stars way off in the distance. Then, as it travels with the Earth for millions and millions of miles, it looks back at that same star. Because Gaia has moved, the star will look like it's shifted a tiny, tiny bit. It's the same effect you get if you hold your thumb out and close one eye, then the other. Your thumb seems to jump, right? By measuring that tiny shift, that tiny angle, Gaia can use basic high school trigonometry to calculate the star's actual distance. It's just genius.
And it does this again and again
and again, at a rate that is just staggering. Get this, Gaia makes over 1.5 million of these observations every single hour. Think about that. After just 4 months, it's already scanned the entire sky at least once. The sheer amount of data, the scale of this operation, it's just mind-boggling. So, after years and years of this relentless scanning, of measuring and calculating, what was the result? What did we get for all that effort? Well, the payoff was a map. A map so detailed, so precise, it completely changed our understanding of our own galactic neighborhood.
So, for the very first time, after triangulating the true 3D positions of over 1 billion stars, scientists were able to put it all together, the Gaia map. And this wasn't just, a slightly better version of the old charts. No. This was a quantum leap forward in our ability to actually see the Milky Way.
And this right here, this is the real game changer. The data from Gaia didn't just give us a prettier picture, it gave us a whole new dimension of information. We can now see the true three-dimensional structure of our galaxy. And that means we don't just know where the stars are, we can see where they're going. We can see their motion, their velocity. We can see the galaxy in motion.
Oh, I absolutely love this analogy. It's just perfect. Think about the great explorers from centuries ago who first mapped our planet, who sailed into the unknown and drew the first real maps of the continents. That is the level of breakthrough we are talking about here. It's like we just hired a team of revolutionary cartographers to make an entirely new, incredibly detailed map of our home galaxy, all while sitting inside it.
And this is where it gets really, really exciting. For the first time in human history, we have the map, a real one. We can see the clusters of stars, we can see these long streams of stars that are like fossil records of ancient collisions with other galaxies. And maybe, just maybe, we can finally start to answer that question we started with: how did our galaxy get its magnificent spirals? The new atlas is in our hands, the real age of galactic discovery. It's really just beginning.